A telescope records a flash from apparently empty darkness. Later, nearby stars show altered spectra. Did the flash change those stars? Or did it change the space between them? That distinction decides whether astronomers found a cosmic event. It may also reveal a much closer deception. A spectrum is not merely a star's color. It is a barcode made from missing wavelengths. Those missing lines expose temperature, chemistry, motion, and surrounding gas. When several stars change together, investigators become suspicious immediately. Distant stars rarely coordinate their behavior. Their shared view through Earth's atmosphere can. Their shared path through a telescope can. And their shared foreground sky can change faster than anyone expects. The first image creates the strongest illusion. An empty point on a sky map is never truly empty. It may contain a faint galaxy beyond detection. It may hide a cold object reflecting almost nothing. It may sit beside an untracked satellite path. It may also be a temporary defect inside the detector. A flash lasting seconds can come from countless sources. A stellar explosion is possible. A distant gamma-ray burst is possible. Even a rock entering Earth's atmosphere can fool instruments. But the later spectral shift supplies the crucial clue. One bright flash and several changed stars seem connected. Science begins by asking whether they actually are. The answer often lies closer than the stars themselves. First, astronomers would test the impossible explanation. Could one flash physically alter neighboring stars? For ordinary stars, almost certainly not. The stars only appear adjacent from Earth. They may be separated by hundreds of light years. Some could lie thousands of light years apart. Light from one transient needs years to cross such distances. It cannot modify several distant stars within 1 week. Is far too short cosmically. That timing eliminates the most dramatic interpretation. The stars did not suddenly change their chemistry. Their light was changed before reaching the observatory. Now the mystery becomes more precise. What can alter many spectra inside one tiny patch? The answer may begin above the telescope dome. Earth's atmosphere is never optically still. It contains water vapor, dust, ozone, smoke, and glowing gases. Each layer absorbs selected wavelengths. Each layer can reshape a measured spectrum. Most corrections work extremely well under ordinary conditions. But unusual conditions can slip through calibration. Thin clouds can scatter blue light more strongly. High-altitude dust can redden an entire field. Smoke can introduce broad absorption patterns. Auroral emissions can add bright lines to observations. A telescope sees through an atmosphere, not around it. That fact becomes dangerous during subtle measurements, especially when the changed stars occupy one small region. Above Earth, air can still glow. The upper atmosphere produces faint emissions every night. This is called airglow. Human eyes rarely notice it clearly. Sensitive detectors notice almost everything. Its brightness changes with solar activity and atmospheric waves. A passing disturbance can strengthen specific spectral lines. Those lines may appear beside every star in an image. At first glance, each star seems chemically altered. In reality, extra light has been added between the stars. Subtracting the sky background usually removes the problem. Usually is not always. A bright transient can trigger different observing settings. Those settings can complicate background subtraction. The calendar itself may be evidence. Why did the strange shift appear after 7 nights? But observatories repeat many actions on repeating schedules. The same target may return at similar local times. The telescope may use the same camera orientation. The stars may cross the same detector pixels. The moon may occupy a related position. Weather patterns may revisit the same air mass. Even maintenance routines can repeat predictably. A 7-night gap does not prove a 7-day physical process. It may expose a repeating observation geometry. The key question is brutally simple. Did another observatory see the altered spectra? If not, the universe may be innocent. The detector is the next suspect. Modern astronomical cameras are astonishingly sensitive. That sensitivity creates unusual failure modes. A cosmic ray can strike a detector pixel. It can make a sharp, bright, false flash. One image alone cannot settle the claim. Astronomers compare separate exposures taken minutes apart. A real sky source stays fixed among the stars. A cosmic ray changes shape or vanishes. Hot pixels can also imitate faint objects. Electronic noise may cluster into convincing patterns. Software can accidentally exaggerate those patterns. The first flash might never have existed overhead, but it could still influence every later observation. Can matter more than an entire galaxy. Spectrographs spread starlight across detector rows. Each row becomes a narrow rainbow. If calibration shifts slightly, spectral lines shift too. If sensitivity changes, line depths change too. A damaged pixel column can affect several targets. So can scattered light inside the instrument. A bright flash may leave a temporary electronic memory. This is called persistence in some detectors. Residual charge can remain after intense illumination. Later exposures may inherit a faint false pattern. The effect may appear only under certain settings. That would explain a delayed anomaly without changing any star. But investigators would need raw data to prove it. Then comes a stranger possibility: reflected sunlight. Thousands of human-made objects cross the night sky. Most are too faint for casual viewing. Some briefly brighten at exactly the wrong angle. A rotating object can produce a sudden flare. A high-altitude fragment can cross an image unnoticed. Its reflection may be recorded as a point. Later, sunlight can contaminate observations differently. A thin cloud can scatter that unwanted light. The effect may look stronger near particular wavelengths. Spectra from nearby stars can acquire similar distortions. This does not require an exotic object. It requires geometry, timing, and a sensitive instrument. Yet one detail would separate this explanation. The flash should move between consecutive exposures. A natural foreground object can create similar confusion. A small asteroid may cross a crowded stellar field. During a long exposure, it can resemble a flash. If it moves slowly, automated software may miss motion. A cometary fragment can release dust or gas. Dust reflects sunlight and changes the local background. Gas can glow at selected wavelengths. However, this explanation has limits. A nearby object rarely changes several stellar spectra identically. It would need to contaminate the observing field broadly. It would also need the right position after 7 nights. Orbital calculations could test that quickly. Sky surveys would search earlier and later frames. An object leaves a path, even when mystery does not. Solar activity rises and falls in broad cycles. But solar effects can change Earth's upper atmosphere rapidly. A solar storm can disturb radio signals and airglow. It can also intensify auroras far from the poles. Those emissions contain recognizable spectral lines. If the observatory points through a glowing region, trouble begins. The stars remain constant behind the glow. Their measured spectra acquire a local atmospheric signature. This can happen unevenly across the sky. One field looks normal. Another field looks chemically impossible. A flash recorded earlier might be unrelated. That is the uncomfortable possibility scientists must accept. 2 rare events can occur near each other. Human pattern recognition desperately wants them connected. The data must resist that temptation. But suppose independent observatories confirm the spectral changes. Now the mystery becomes genuinely astronomical. the changed stars would still not need changing themselves. Something could lie between Earth and those stars. Imagine a thin veil of gas crossing our line of sight. Gas absorbs specific wavelengths of starlight. Its chemical fingerprint appears in every background source. If several stars sit behind that veil, lines deepen together. The stars may be unrelated. The absorbing cloud is the shared object. This happens throughout astronomy. Interstellar gas leaves signatures in stellar spectra. But a rapid change would demand an unusual foreground structure. It would need sharp edges or rapid motion, and it would need to cross a tiny angular field. The scale becomes surprising here. Interstellar clouds move fast by human standards. They still move slowly across the sky. At typical distances, their apparent motion is tiny. A cloud edge crossing several star positions takes time. Often that means months, years, or far longer. They would favor much closer. It could be material inside our solar system. It could be a tenuous cloud near Earth. It could even be plasma shaped by magnetic fields. It bends and delays radio waves strongly. At optical wavelengths, effects are usually subtler. Still, ionized material can scatter and emit light. The measurements would need extraordinary care. A real result would be rare, not impossible. There's roughly low Earth orbit altitude. At such distances, objects move rapidly across the sky. A diffuse exhaust cloud could spread after an event. It might be nearly invisible in direct images. Yet spectroscopy could detect added emission. Rocket exhaust contains molecules and particles with known signatures. A spacecraft maneuver can create a temporary cloud. So can a fuel venting event. The cloud would drift, expand, and fade. Its path could cross several apparent stars. 7 nights later, it might reach another geometry. This explanation is testable, not sensational. Observers would compare predicted orbital paths. They would inspect all sky cameras and satellite records. The sky above an observatory contains more infrastructure than darkness. There is also a problem hidden in the word nearby. Nearby on an image means nearby in angle. It says nothing about distance. One star may be away, another may be away. A galaxy may sit vastly farther behind both. If every spectrum changes identically, foreground contamination becomes likely. If each spectrum changes differently, the puzzle deepens. Perhaps only blue wavelengths changed. Perhaps absorption lines shifted by the same amount. Perhaps one new emission line appeared everywhere. Each pattern points toward a different cause. Identical shifts suggest calibration or motion. Identical new lines suggest added foreground light. Different changes may indicate separate stellar behavior. The shape of the anomaly matters more than the headline. Astronomers would rebuild the event from the beginning. They would retrieve untouched detector files. They would inspect weather logs and dome conditions. They would check the telescope's pointing history. They would compare calibration lamps before and after observations. They would examine dark frames and flat fields. They would search nearby images from other nights. They would ask whether the moon was above the horizon. They would measure airglow lines in blank sky regions. They would check satellite predictions and space weather records. Then they would contact distant observatories. A true celestial event should survive independent instruments. An instrumental ghost usually dies under that test. This is how mystery becomes measurement. Can transform a strange claim. If both see the same flash, confidence rises sharply. If both see matching later spectra, confidence rises further. If one sees nothing, location becomes the clue. A local atmospheric effect affects only one region. An instrument defect affects only one system. A satellite flare affects observers differently across Earth. A distant event should appear from almost everywhere. Timing differences can reveal the object's distance. Parallax can separate near-Earth events from distant ones. Even a non-detection provides valuable evidence. The absence is not empty. It narrows the list of possible worlds. Sometimes the universe answers through disagreement. The most unsettling outcome is also the most useful. The flash may be real. The spectral changes may be real. And they may have no connection whatsoever. One may be a distant transient. The other may be high-altitude airglow. Their coincidence creates a story before evidence does. That is why observatories distrust beautiful explanations. Nature does produce astonishing linked events, but instruments, weather, and orbital traffic produce coincidences too. The task is not to protect wonder. The task is to locate it accurately. A blank patch of sky can hide a galaxy. A changed spectrum can hide an earthly cause. Which hidden layer would survive every test?